Earth, some might say, is seriously old, over 4.5 billion years in fact. It's difficult to fathom how long this is, especially when our own lives can seem so long. However, consider this. If the Earth began at midnight on a 12-hour clock, it's not until 11:59 and 50 seconds that modern humans, or Homo sapiens, came along, which was still around 130,000 years ago. So let's return to the creation of Earth. Midnight, or 0 hour, 4.6 billion years ago. The Hadean era saw our world in a state of constant geological flux. The conditions were hellish. Earth was like a giant fireball. Hydrogen and helium gases combined with other lighter elements to form a volatile atmosphere, while heavier elements, such as iron, descended to the Earth's core. A molten surface with enormous volcanoes generated incredible heat. There was no oxygen or bacteria, so it was impossible for life to exist. Nitrogen and carbon dioxide gases, along with water vapor, spewed from the volcanoes into the atmosphere, a process called outgassing. Some 20,000 asteroids struck Earth during the Hadean era, creating large craters, similar to those on our moon. 700 million years pass, or 1 hour and 52 minutes, before the Earth's crust becomes marginally cooler and more solid. The Archean era was characterized by shifting continents and oceans like a thick molten soup, as well as the production of small amounts of oxygen. Debate continues over what Earth was like during this 1.3 billion year era, or 3.5 hours. The continental plates, which we often hear about during earthquakes, are thought to have been highly active. Some believe they melted and eroded so rapidly that the formation of a stable crust would have proved difficult, so only mini-continents were possible. It's likely that some life form existed throughout the Archean era, but may have been limited to simple single-celled organisms called prokaryota. The following era was the Proterozoic, which lasted nearly 2 billion years, or over 5 hours, and was dominated by the formation of a supercontinent. This giant landmass was made up of small cratons with large island arcs. The supercontinent eventually broke apart, drifting into a formation which resembles today's continents. Geologists have discovered Proterozoic rocks on every continent. The rocks contain metallic ores, minerals such as iron, gold, copper, uranium, and nickel. Perhaps most importantly, many of these rocks show traces of primitive life forms, including blue-green algae and the first oxygen-dependent animals, the Ediacara fauna. Minute evolutionary changes, spanning millions of years, were evident in marine life, which bloomed in the Paleozoic era. It was a relatively short but very eventful 47 minutes, or 300 million years. This explosion in marine life led to many new species, such as the horseshoe crab, which are found in the rock strata of empty seabeds. Vertebrate life forms also made the transition from sea to land. They overcame their dependence on moist environments and began breathing air. The most dramatic change was the laying of reptilian eggs with protective shells. Flight also became possible as insects evolved wings. The Paleozoic era ended with the largest mass extinction in Earth's history. The Great Dying saw marine life completely devastated by methane from the ocean floor, while massive coal and gas fires erupted on land. It is also the only known mass extinction of insects. However, given the right conditions, life has always shown its ability to return. The Mesozoic era saw the appearance of the major plant and animal groups that still exist today. It spanned nearly 200 million years, roughly 30 minutes on our clock. Although the era is best known for the extinction of dinosaurs, the conditions that made life flourish in the first place are perhaps more revealing. Temperatures were generally warm and stable. The first true mammals, which were small omnivores, sprung to life. Eventually, lizards, turtles, and flying pterosaurs emerged. Fish, sharks, and other large reptiles also swam the Mesozoic seas. During this time, the continents also began to move into their present-day configuration. The Mesozoic era concluded with a mass extinction that devastated most life forms. All marine reptiles died. On land, the dinosaurs and flying reptiles also became extinct. Many theories exist about what caused this event. An asteroid striking Earth is the most popular, though the draining of continental seas, intense volcanic activity, or shifting tectonic plates are also possibilities. The Cenozoic era, which began 65 million years ago, was vastly different to the Mesozoic. The name means new life, and the key evolutionary trait of this life was adaptation, especially among mammals. The ability to adapt in different environments, now empty of dinosaurs, led to many smaller mouse-like animals evolving into elephants, lions, horses, and the great apes. The seas filled with whales, dolphins, and sharks, the skies with large bats and eagles. Life was again devastated by a major extinction event, which occurred around 10,000 years ago, killing off many Ice Age mammals, like the woolly mammoth. The final seconds in the current Cenozoic era welcomed us. And it's only in the last fraction of a millisecond that we've actually made these discoveries about Earth's epic history. Exactly what future Earth will look like is anybody's guess. Time will only tell. An apartment building is constructed floor by floor, like layers, up to the highest floor. The first floor constructed is the basement, and then all the other floors are laid on top. The top floor is constructed last. This is the newest. The layers of the earth are constructed in a similar way. The most recent layers of rock and sediment are at the top, while the oldest are at the bottom. This formation, which provides evidence dating back billions of years, helps explain the planet's various life forms and their evolution. So what are some of the methods archaeologists and geologists use to do this? Relative dating determines the sequential order of past events, such as the order in which rock layers, called strata, formed. It does not give an absolute age of the rocks or the fossils often discovered inside. Fossils are traces of animals, plants, and organisms preserved in the strata. They provide us with valuable information about ancient life on Earth. Throughout the 19th century, scientists using relative dating techniques were able to make estimations on the sequential age of fossils. They created a stratigraphic column, with each division of geological time being characterized by the same fossils. It didn't matter geographically where these fossils were located. The same patterns appeared in the same layers, allowing scientists to determine the relative age of newly found fossils. In the 20th century, scientists honed their skills and were able to determine the age of fossils by measuring the decay of radioactive isotopes contained within them. This is called absolute dating. The method most widely known among the general public is carbon dating, mainly because the younger end of its age range overlaps with human history. carbon dating is used to date organic remains. A living organism has a predictable ratio of the stable carbon-12 isotope to the unstable isotope carbon-14. Carbon-14 is formed when cosmic rays from the sun interact with carbon in the upper atmosphere. While the organism is alive, the unstable isotope carbon-14 is continually replenished via the carbon cycle, maintaining this ratio. When an organism dies, carbon-14 atoms that decay are no longer replaced by newly made ones, and the number of carbon-14 atoms decreases. This happens at a constant rate. The time it takes for half the original number of carbon-14 atoms to decay is called the half-life. The half-life of carbon-14 is 5,730 years. Over this time, the number of carbon-14 atoms will halve and will continue halving every 5,730 years. After about 50,000 years, there will be no detectable carbon-14 left. By comparing the number of carbon-14 atoms in organic remains to the number of atoms of the stable isotope carbon-12, scientists can determine the fossil's age. However, carbon-14's relatively short half-life means dating is only reliable for materials that are less than 50,000 years old, and they must contain carbon. Examples are charcoal, bones, animal and plant remains. But 50,000 years is a very short time in geological history. Most rocks are millions to billions of years old. To measure such old ages, geologists must use very slow radioactive decays. The decay of uranium to lead can be used to date minerals and rocks with ages from a few 100,000 to billions of years. Based on the decay chain where uranium-238 decays to lead-206, it is useful for dating igneous rocks containing uranium-based minerals. Uranium-lead dating is the best and most commonly used method for absolute dating in geology. Potassium-argon dating is another absolute dating technique. It is used to date igneous rocks that contain potassium-bearing minerals, such as feldspars. One of the 3 potassium isotopes is potassium-40, which has a half-life of 1.3 billion years. It decays into one of the isotopes of the element argon and accumulates in rocks after they solidify from a molten state. The second isotope, potassium-39, is stable and does not decay. By measuring the ratio of argon-40 to potassium-39, an absolute age of the potassium-bearing minerals is obtained. Potassium-argon dating was famously used to date rock samples taken from the moon during Apollo missions in the 1960s. It also has proved a useful tool for dating the origin of human ancestors in East Africa. In this volcanic area, bones of the oldest hominids were preserved in volcanic strata, which contain potassium-rich minerals. A further method for absolute dating is rubidium-strontium. Rubidium-87 is an unstable isotope which decays into the more stable isotope strontium-87, but does so at a very slow rate. The half-life of rubidium is 50 billion years. Like the uranium-lead technique, rubidium-strontium can be used to date very old rocks. The oldest rock we can walk on today, the Isua sequence in Greenland, is 3,800 million years old and was first dated with rubidium-strontium. Recent advances in molecular technology have given scientists more precise fossil dating methods. Electron spin resonance measures the trapped electrons in fossils. They accumulate in crystalline rocks as a result of low-level natural radioactivity occurring at fossil sites. Measuring current radioactivity levels in soils around fossil sites and comparing them with ESR measurements of fossil material is a highly accurate dating method. Fossil dating methods are undoubtedly complex, and there is constant scientific debate about which are more accurate. Any reliable dating method should compare favorably with another. In other words, 2 dating methods should produce a similar result within their normal margins of error when applied to the same sample. In 1998, a near-perfect transitional fossil was discovered. It was a water vertebrate, fossilized precisely as it was evolving into a land vertebrate. At 370 million years old, the fins of the fish were more like arms and legs, and capable of something close to walking. As technology advances and dating methods become increasingly sophisticated, we are able to piece together a more accurate history of life on this planet. But with knowledge comes more questions, and the more we know, the more there is to find out.
Evolution, according to naturalist Charles Darwin, is like a tree branch.
In illustrated form, the structure can represent evolutionary relationships, such as common descent and divergence, or separation of living and extinct species. A similar diagram, called a cladogram, helps us understand the journey of the hominid, from the early Australopithecus 4 million years ago to us, modern Homo sapiens. Focusing on physical and behavioural traits, we can see how different hominid species adapted to food availability and climate.
Frequently, a change came down to a single, seemingly minor trait, which created a fork in the evolutionary branch. For instance, our common ancestor is the chimpanzee. But how do we know this? While our DNA is remarkably similar, there is one piece of evidence which clearly links us.
Chimpanzees and humans have a larynx that repositions itself during the first 2 years of life to a spot between the pharynx and the lungs.
This gives both species the ability to communicate using sounds. But as humans, it's through our specialised use of language, which evolved across thousands of years, that has helped us explain where we came from and how we got here. The split between our early ape ancestors and hominids occurred when Earth became drier and colder, with less forested area and more open spaces.
First on the scene were the Australopithecus family, which included the Anamensis, Afarensis, and Africanus. All three were small and fine-boned and lived between 4.2 and 2.5 million years ago. Males weighed around 40 kilograms and were about 1.5 metres tall, while females were a little over 30 kilograms and about 1 metre 20 in height. Remarkably, the fossil remains of the earliest of these, the Anamensis, indicates it was bipedal, or walked on 2 feet. Even though this is eventually what gave our hominid ancestors their advantage, bipedalism is also observed in the great apes, where they compete for food or territory.
Despite its strength and stamina, the Africanus was hunted to extinction by Dinofelis, a huge saber-toothed cat, throughout Europe, Africa, Asia, and North America.
Around 2.5 million years ago, the Australopithecines are thought to have split into the genus Homo. This new branch produced modern Homo sapiens and the Paranthropus. The Paranthropus family consisted of the Aethiopicus, Boise, and Robustus.
The Boise and Robustus descended from the Aethiopicus and lived in East Africa for over 1 million years. The Boise, particularly the males, had huge chests and large grinding teeth. Despite their clever ways of exploiting jungle areas, such as their taste for termites, the Boise were driven extinct by an intense period of cooling and drying during the Ice Age. Also in East Africa, at the same time, existed Homo habilis. Nicknamed Handyman, habilis is often described as the earliest ancestor to Homo sapiens. The change in diet from plant to meat is often considered the main reason why brain size increased with habilis.
Meat is easier to digest, and this reduced the need for large intestines, allowing energy to be diverted for brain development. Fossil records show habilis developed crude tools for cutting through animal hides and smashing open bones to extract the marrow inside. Around 2 million years ago, Homo erectus, or upright man, evolved from habilis. Upright man had to travel long distances to scavenge for food. In order to conserve more energy for upright walking, erectus developed a narrow pelvis.
This single anatomical change had a profound impact on human relationships.
As brain size increased, mothers delivered larger-brained infants through a smaller birth canal.
The solution was a trade-off, and babies started being born at a less matured stage. This meant they were completely helpless and relied entirely on their mothers for nourishment. The mother also required special attention, and so both became dependent on the male partner for their care.
Many experts see this evolutionary shift as the beginning of the nuclear family. Erectus's direct descendant, Homo heidelbergensis, or Heidelberg man, first appeared between 800 and 600,000 years ago.
Heidelberg man was more intelligent than Erectus and used speech to communicate basic needs.
Its population spread from Africa to southern Europe and Asia, but the harsh conditions took a huge toll and their numbers dropped rapidly.
Aside from Homo sapiens, the most famous of all the hominids is undoubtedly the Neanderthal.
Homo neanderthalensis appeared between 200,000 and 300,000 years ago, populating large parts of Europe and the Middle East.
They became extremely muscular to deal with the difficulties encountered during the Ice Age. They looked out upon the world from beneath a bony ridge that arched across their foreheads.
They also developed a useful facial feature. Their long, projecting nose protected delicate brain tissues from the frozen Ice Age air. Social relations and protection of their young were vital to Neanderthals.
Despite the term Neanderthal often being used as an insult, their brains were identical to any modern human.
The exact timing of Homo sapiens' arrival is still debated, but sometime between 150 and 200,000 years ago, we emerged in Africa, a descendant of Heidelberg man. Modern humans developed highly crafted tools, efficient food gathering strategies, and complex social structures. While it's commonly accepted that sapiens and Neanderthals battled for territory and food, new evidence suggests that they mostly coexisted and actually bred with one another.
Erectus was our biggest challenger, especially in India. They were agile hunters and didn't mind eating the odd Homo sapien. However, sapiens were able to outthink their rival using stone-tipped spears, which Erectus hadn't invented. With a population growing towards 7 billion today, Homo sapiens have not only survived, but flourished. However, geneticists are beginning to question some of our fundamental views on evolution and our own origins.
Rather than as a branch or diagram that follows separate and distinct paths, it's more like a chaotic web.
Species, including many in the hominid family, would have crossbred, creating a variety of hybrids. Human history, it seems, isn't so straightforward and will remain a mystery for some time to come.